Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 1 of these recorded sessions. So today we'll be going over for most of y'all Chapter 1 and in general structure and bonding. So how is this going to work? So first of all, we'll have an agenda, right? We'll follow the agenda. It'll have topics and then it'll have questions. And you'll see later, I'll show you the agenda, that we'll have titles on each page reduced so you can, fast forward or go back and be able to find those spots. Or if you just want to focus on one topic, we'll go over that. And basically, each of these videos for Organic Chemistry 1 and even 2, um, pretty much it'll cover the entire chapter. So we'll pretty much, for Organic Chemistry 1, we'll focus on one topic at a time, and after each topic that we cover, we will have questions if we need it. So if we don't need it, obviously we're not going to waste our time asking questions because, again, either it's already on the topic, so it's pretty straightforward, like definitions, things like that, or if it's like reviews from Gen Chem, things like that. So here is our agenda. As you can see, part one, organic chemistry one, right? Structure and bonding. We're going to go over the atom, the periodic table, bonding, and you see those don't have asterisks, so they don't have questions at the end of them, because again, the review, right? And then we'll go through valence electrons, formal charges, isomers, resonance, hybridization, and molecular geometry, and condensed skeletal structures, and bond polarity. So then those will have questions. So again, will be, this is a summary, right? This is not a substitute for a lecture or class. Um, this is just what I feel like the main points of each chapter. So if you have any questions on any of these, scroll over, or if you want to watch the whole video and get these practice questions in, then do that as well. Okay, so let's get started. First things first, what are we going to talk about? The atom, right? And chapter one is very Gen Chem heavy, and you kind of see why we don't have questions in the first few topics because they're all Gen Chem, and even below Gen Chem because the atom, we know what the atom is, right? We know we can get the atomic number from it, atomic number, right? And then we can get the mass from it, right? By adding the proton plus neutron, and the atomic number is just the electrons, right? So nothing too crazy. So now let's introduce some vocabulary that you guys should be keeping track of throughout the class, right? Isotopes, atoms with different number neutrons, right? Different number neutrons, we know that. Isotopes, and now the probably the most important part, ions, and you guys probably know these already, cations and anions, right? Positive and the negative. Cations, anions. Cations are positive, anions are negative. And that's all because of electrons, right? Cations have less electrons, anions have more electrons. Um, so loss or gain of electrons. Right, so boom, one topic done, just a quick review, right? So now I'm going to move on to the next topic, which is the periodic table. And again, another easy one, pretty straightforward. We know the periodic table, of course, has all the elements. We can show the trends, things like that. And as we go, we will keep adding trends. But for now, I don't think in this chapter we have too many trends, or if anything, the electronegativity, right? But other than that, as we go, we'll be keep adding more acidity, nucleophilicity, things like that. And sometimes they even like coincide. So it's always good when things repeat or kind of overlap because then less things to study, right? So we're all for studying less, right? Okay. So what happens if the elements are in the same row, Same row means similar size. What about same column? And these aren't very like hard spells, they're not super complicated, but again, just keeping this in the back of your head, you can kind of, if you have to, you can guess, have an educated guess if you don't know something, right? So that type of thing, you're not going to get asked what happens in the same row, right? Like all straight up like that. But you can kind of use that in the back of your head and kind of think, okay, if these are in the same row, we know for sure they're similar size. So similar size, what happens with the ring size, orbitals, things like that. So you can kind of keep connecting dots and make that educated guess, if anything, right? Similar column we have, or I mean same column we have similar physical. Oh, did I spell physical wrong? Physical and chemical properties, right? So again, same column, then you start thinking about, okay, boiling point, melting point, solubility, things like that, and that's what the physical and chemical properties are. Okay, now let's talk about, with the periodic table still, atomic orbitals, right? And we'll even go into depth into these once we get to hybridization. So we have S for sphere, right? P for our peanut shape, right? D for daisy, F for funky, right? So something like that. And then funky, right? So, and this also ties into electron configuration, like 1s2, 2s2, 2p, whatever, right? So, and that was mostly, we did that a lot in Gen Chem, so hopefully you guys don't forget that, electron configuration. But we're not going to be using that a lot in OChem, but in this first chapter, there's a couple questions on it because, again, this is like a review of Gen Chem, what you guys should have gotten out of Gen Chem. Config, right? So, again, that's it with the periodic table, right? Fast summary, that's all you need to know. Keep in mind, right? Keep in mind. And now let's move on. What's our next topic? Bonding, right? So, again, if you have topics you want to get to, or I always I suggest that you watch the whole video because as each topic goes, there's going to be questions. So you don't want to miss those practice questions. Practice is key in OChem. So keep that in mind. Practice, practice, practice. Wherever you get the practice questions from, um, do them, right? Okay. So of course we have ionic and covalent, right? So ionic is a transfer of electrons, and we'll be doing a lot of that later in the semester when we start talking about reactions, and then sharing of electrons. But again, a review, right? Knowing what these are. Okay, and that's pretty much it, right? And I just wanted to touch upon this because, again, we're pretty much just going down the list of the chapter, right? Going down the list of the index of the chapter, so we don't want to miss anything, even though they're just like small little part, but let's be consistent. So now, valence electrons. Valence electrons. So, pretty much all you need to know, predicted number of bonds equals 8 minus number of valence electrons. Number of valence electrons. So again, let's say we have Bokhanov, right? We have what? 5, 4, they're groups, right? 3, 2, one, right? And pretty much predicted number of bonds is their neutral form. So let's look at carbon for instance. 8 minus 4 is 4. So we know carbon's like 4 bonds, so that's the neutral. So it's gonna have 4 bonds. Let's do nitrogen. Nitrogen likes what? 8 minus 3. It's gonna like um, again predicted number of bonds, right? It can get up to 5, things like that. So you know, kind of it's the groups, right? And pretty much also how many valence electrons around it as well. And you can kind of see here, it ties in with the Lewis structures, right? Lewis structures, and to draw them, we need what? Only valence electrons are shown octet rule, and hydrogens only have, doesn't follow the octet rule, obviously, it only has 2 electrons, right? So let's put this to the test. Now we're going to be going on to the questions. Electron. So first, draw the valence electron, the Lewis structure. Draw Lewis structure of CH3CO2H, right? And this is another question. So I'll give you a couple questions at a time, and then you can pause and do them, right? Which are correct? We have this, we have, hopefully they'll all fit, this, and then I'm going to go up here. This one, or so. So I'll give you guys a couple minutes, pause the video, and try and do these questions. Okay, so I'm going to change colors. For the first one, draw the Lewis structure of CH3CO2H. So you should have gone something like this, right? We want to show, oops, this is an H. We want to show all the carbons and the hydrogens. We want to show all the ones with the octet rule, right? And that's what we have, right? So we have the lone pairs, the valence electrons shown. We have all the H's, all the carbons. It looks like we're good. Are there any charges? No charges, so we're good. So what about um the second one? You guys should have gone this one, a correct one, and this one as the correct one. Because this one, it's missing what? It's missing this charge here, right? And this one also missing those charges, right? These would have been what? Positives as well, right? So charges, to be a complete Lewis structure, you need everything. Lone pairs, right? All the valence, and then charges if they have them, the ions, right? Okay, so now, since we're talking about charges, let's move on to formal charges. Okay, formal charges. So formal charge will abbreviate as FC equals number of valence electrons minus number of owned electrons. So what does owned mean? So ownership. So if they're a lone pair, that atom that has a lone pair have the full ownership. If it's a bond, it's pretty much half and half, half for that atom than the other atom, right? So let's do questions for formal charges. And this one's a short one, so we'll keep that up here. So this one, first question. What is the formal charge of this carbon? So formal charge of this, right? And then second question over here, same thing. What is the formal charge? CH3, CO2 minus. What is the formal charge of this carbon and this carbon? So again, pause the video, take your time, look over your notes and try and see if you can find the answer. Okay, you guys are back. Let's see what you guys got. So for this one, let's just follow this formula, right? Fc equals number of valence electrons. For the carbon, we have 4 minus number of owned electrons. So again, it has lone pairs, so it has full ownership of that, right? 1, 2, and then it has bonds over here, so it'll have half ownership of that. And we know bonds have 2 electrons each, right? So 1, 2, 3, 4, 5. You guys should have gone -1, right? So now let's do this one, the second one. This is a little bit different because it has a this is an overall charge, right? Not um the charge of this carbon or this carbon, right? This is the overall charge of the molecule. So what do? The best thing here for me is to draw it because then you'll see how many bonds there are. So kind of turn it into what this would look like, right? So CH3, H, 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 right? CH3, C, and then 2 oxygens, right? O, O, right? So now you see where that negative charge is, right? This this negative charge, this negative charge, and you see how none of the other carbons have any charges, right? Because this is what 4 minus it owns 1, 2, 3, 4, 0. Same with this one, right? Also 0. So that charge wasn't from the carbon, it was from this oxygen. And you'll learn how to draw these um, a little bit later. But again, this is summary, and this is kind of just this is in kind of we're doing this knowing that you guys have gone through the chapter yourself, right? So this is kind of like a big review. So yeah, and again, you can get the formal charge for each one of these atoms. So that's another thing with that. Okay, now let's move on. What's our next topic? Our next topic is isomers. So isomers, this is just going to be very shallow, very straightforward. So we know isomers are same molecular formula, molecular formula, different molecules, right? But you'll find out, and I'm kind of just gonna um put this in because you'll see it later, but it's further down the semester. But kind of to give you a heads up. Let's see, differ atoms, electrons. So we have two kinds of isomers. We have constitutional, which is the one we'll be focusing on because it's the most straightforward, constitutional. And then we'll have stereoisomers. So constitutional is the structures, they have same molecular formula, but the structures are different. Structures differ. And in stereoisomers, 3D, 3D as in like um, cis, trans, things like that. And that's why this is gonna come up later because you guys haven't heard of R and S configuration, right? So pretty much in 3D space, right? They're twisted differently, or they're pointing. It was pointing up, now it's pointing down, right? That type of thing. So 3D orientation differ. So that's why it's going to be a little bit later when we get to stereoisomers because we don't know, we haven't talked about RNS, cis and trans, things like that. But we're going to be focusing on constitutional, which is where the structures completely different. And I have a couple of questions here for isomers, and this is going to be about constitutional. So draw isomers of C2H6O. And then I have another one. Which one of these, which ones are isomers out of these three? CH3, 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 CH2, OCH3, CH3, CO, CH3. Okay, so pause the video, take a minute and see what you guys come up with. Okay, so for the first one, isomers of C2H6O. So pretty much, what molecules can you draw that has two carbons, six hydrogens, and one oxygen, right? So you guys should have gone something like this. One, and two. So you guys should have had two isomers of C2H6. And these are carbons, right? And then we know there's hydrogens on them, so we can draw them, right? And we'll learn a little bit later. So we're going to review how to draw these. So, and that's OH right there. This is a carbon. This is a carbon. That's two H's over here, right? And we know how many hydrogens there are because it's neutral, right? And carbon's like four bonds, so there's nothing. It's not missing any of the bonds, or it's not. It doesn't have an extra bond because it doesn't have a charge, right? Okay, so for the next one, which are isomers, you guys should have gone on these first two, right? Because both of these have three carbons, right? Eight H's, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, right? And then how many oxygens and one oxygen, right? This one is missing hydrogens. It's missing two hydrogens, so it's not an isomer. It can't be an isomer. And that's it. Same molecular formula, but like these two, same molecular formula, but different molecules, right? So this is constitutional. Constitutional. So, okay. Now, what's the next one? Let's move on to resonance. And resonance is probably the biggest deal for this first chapter because this will come up um, later in OChem 2 and a little bit in biochem. So, might as well go over it now, right? So, first things first, we know what resonance is: delocalization, delocalization of electrons. So meaning if they were in a pi bond, right? Pi bonds can be delocalized because those are just electrons. Sigma bonds cannot because they're fixed, right? Because if you delocalize them, then that means you're breaking them. So we're not breaking anything with resonance. We're just delocalizing. Um, Charges, right? So anions, negative charges, and radicals. We don't really see radicals a lot, but you can resonate them because they're just pretty much one electron, right? You can resonate that. So first things first, resonance structures are not real not real, right? Only the hybrids are. Hybrids are real, right? So resonance structures, I always like to um, explain them as resonance structures are snapshots, are pictures, right? You take a picture and you're frozen, right? Picture, picture, picture. And those are what resonance structures are. But hybrids, they're dotted lines, right? That means they're moving back and forth forever, right? So it's like a GIF, right? So it's like keep going back and forth, right? Back and forth compared to pictures. So pictures and GIFs, right? Okay, so that's that. Second, resonance structures are not in equilibrium. Equilibrium, right? Because again, there's that movement of electrons, and in equilibrium, in structures, there's no movement, right, of electrons, because we said what? They're just pictures, right? Third, structures, and again, don't confuse structures and hybrids. Structures are just the snapshots, which is what we usually work with, and the hybrids are the ones with the dotted lines, right? I should put here dotted lines, so don't get confused. Structures are not isomers, right? Because they don't differ in structure, right? We said isomers they have the same molecular formula but differ in either structure or their orientation, right? Which is pretty much the structure as well. But this one, they only differ in electrons, right? So it has to be both electrons and structure. Different, different electrons only, right? So that's what resonance is. And I have a few questions for you guys for resonance. And yeah, depending on who you have as a professor or what type of test they like, sometimes multiple choice, that's always great. Sometimes um, they like for you guys, you know, short answers, which is tough. So depending on who you have, they might really grill you on resonance. But if it's multiple choice, it's gonna be pretty easy to get through it because I mean, as long as you know what resonance is and you have the choices, you can pretty much narrow it down. So, but in this case, I'm gonna make you draw it because so I don't have to draw a lot. So I don't have to draw the choices, right? So find me a resonance structure of this, right? So making you draw. And then this one, I have to give it to you. Rank in order of decreasing importance of resonance hybrid. So we have this one, and then this one. So take a couple minutes, pause the video and see what you guys get. So I forgot to mention resonance. What do we care? Why do we resonate? Why do we delocalize those electrons? It's all about stability. So if you hear resonance, it should be synonymous with stability, right? We resonate because we like to be stable, right? Stability. So with that being said, let's answer these questions. Let me change my color. Okay, so this one, you guys should have given me something like this, right? So what happened? Again, we can resonate what? Pi, negative charges, pi bonds, negative charges, and radicals. In this case, what do we have? We only have that pi bond, right? So we could resonate it up here, and you'll see later as we're gonna talk about this why we moved it up here. Um, so that means again these are just electrons. So obviously this will end up with a negative charge now because it has extra electrons, right? And this lost its bond, so obviously it's going to be a positive charge because it's missing its electrons, right? So that's why we get those charges. And now for this one, you guys should have gone the importance as this, this. So this first one is more important than this one, right? And why? So as we said, we're all about stability with resonance, right? So you see here, it's neutral, neutral, happy, no charges, right? This one, two charges. This one, two charges. So pretty much the rule of thumb is, and I'm going to do this in a different color as well, the more charges equals less stable, right? So this has two charges, right? And these has two charges. So between those two, now how do we differentiate, right? Both of them have two charges, so what do we need to do? Now we look at stability again, right? Which one of these is more stable holding those charges? So let's look at oxygen because on the middle it has the negative charge. On the right side it has a positive charge. So why did we prefer it with the negative charge versus the positive charge? Well, as we know, oxygen is very what? Electronegative. So as an electronegative atom, will it prefer negative charge or a positive charge? A negative charge, right? So I'm electronegative. I like electronegativity. I like negative charges, right? So that's why we chose the electronegative charge. I mean the negative charge on the electronegative atom because it just makes sense because it can handle it. And you can even do that with the carbon, right? This carbon over here. This carbon is not very electronegative, so it's not gonna mind. It's gonna be better with the positive charge than with the negative charge, right? Think of it as um, kind of like, okay, I'm an oxygen. I can handle this negative charge because I'm electronegative, right? I can just take them, and I like electronegative. I like negative charge because electronegativity is all about pulling your charge towards you, right? So think about that. So electronegativity plays a part, and always kind of think of that when, especially heteroatoms, right, have charges. So does this heteroatom, would this heteroatom like this charge compared to this heteroatom or carbon, right? So that's what you have to think about. Okay. So yeah, resonance is a big deal, right? But it's all about, at the end, it's all about stability. So now let's move on to our next one, which is hybridization, and this one's a good one too. Hybridization and molecular geometry. So pretty much hybridization, combo of two or more orbitals to form the same number of hybrids hybrids. So pretty much same shape and energy. The big thing here again, hybridization, the sp1, sp2, sp3. things like that, and what happens. So let me see if I can fit this into one page so we don't have to go too much, and this should be quick since this is a review, right? So pretty much sp3, let's do sp3. Let's say I have a CH4, right? What's what's the hybridization of this carbon? How can we find out that it's really sp3? So first, we have to go um, find out its electron configuration, and it happens to be 1s2, 2s2, 2p2, right? But in hybridization's case, we care about the outer orbitals, right? The outer orbitals, because those are the ones that are bonding, right? The outer shell is the one that's bonding to other atoms. So we can scrap this one, right, and just focus on this. So now we have 2s, and we know 2s has just max of 2 electrons, and then the 2p max of 6 electrons. But in this case, this one has 1, 2, right? And 2p also has 1, 2 because it's 2p2, right? So it has 2 electrons in the p orbital. So now I'm gonna have to change colors because this is where it gets hybridized. So hybridized is basically spreading out the electrons, right? So in this case, one of these electrons is gonna go over here. So now it's over here, right? And that's where we get the sp3, right? So we have 1s, and now we have 3p's, right? All of them are taken. So p, p, p equals sp3. And you do the same thing with double bonds and triple bonds, right? And there's also another way to do this is that you can use the group method. Group method. So basically, how many groups does this have? 1, 2, 3, 4. So 4 minus 1 is 3, and sp3. So group method, right? So number of bonds, pretty much. Number of bonds minus 1. And this is 4 bonds, right? Minus 1 equals 3. And we also have another method, another method, which is my favorite one because it's the most, it's how I learned it. So this third one is pretty much sp3. This one's a little bit tricky because it doesn't always work all the time. The groups one work, and actually, the groups one I'll um, tweak. Bonds or lone pairs. Lone pairs. They count too, or lone pairs. Groups is the most, I guess, safe, but I learned it with this method, sp3 minus number of pi bonds. And you see how this works? Because this CH4 doesn't have any pi bonds, right? So sp3 minus 0, sp3. So this is how I learned, but you can use groups, or you can even do this if you want. So let's try this with sp2. So again, hybrid, because I thought I was going to be able to, oh, sorry about that. I thought I was going to be able to fit it all on one page, but that didn't happen. Okay. Hybridization. And we'll get to the molecular geometry like soon. So now let's go to sp2 and see what's up with that. So pretty much same thing. So let's say we had C, this one. and we're looking for C as well, right? So again, carbon has one S2, two S2, two P2. So cross that out. We have S, right? And then the P. We have two in the S, two in the P, and again hybridized, right? Hybridized. But now it's still sp3, right? We have one S and two P's. But the special thing about this is that one of these electrons reserved for pi bonding, pi bond. So now it's reserved, right? So we can't touch it. So now it has one S and then two P's, sp2, right? And let's not do sp3 with another page, but pretty much um we reserved one electron for the pi bond for one pi bond, and for a triple bond we'll reserve two pi bonds, right? Reserve for pi bonds, reserve times two for triple bond, because we know triple bonds have two pi bonds, right? So that type of thing. But then again, you can still use the group method. This one has, right, three groups. So 3 minus 1 is sp2, right? And you can use the sp3 method. And I'm color coding these, so sp3 minus number of pi bond. This one has one pi bond, so we have sp2, right? So whatever method you want to use. Okay. So and that's just a little bit. Not all professors kind of do it that way. They don't show you the concept behind it. So it's kind of fun, kind of seeing it because it looks very complicated, but it's not really, right? But the meat of it, this is the meat of it, and this is like a summary chart. Molecular geometry. So we know how to find sp3, sp2, sp1, or sp, right? So now sp3, sp2, sp. Now each of them have different shapes. So sp3 is called tetrahedral, sp2 is trigonal, sp is linear. And with all these shapes, they all have their angles. So linear obviously is 180 degrees. Oh, I don't know why I parenthesized that. Trigonal is 120. Tetrahedral is 109.5 degrees. And this one's the stability standard. It's the most stable bond angle. Most stable. So pretty much once you start deviating from 109.5, you start getting strained, right? So, and there's also special ones is when you have lone pairs. So let's put here sp3 with one lone pair. You'll end up with a trigonal pyramid. Trigonal pyramid. So watch out for those lone pairs, right? And for sp2, you'll end up with a bent shape. So it's just bent. And there's nothing for sp, right? And for two lone pairs, sp3 will the shape will end up bent, and there's nothing for these two, right? And then just to kind of, you know, you guys probably want to make your own chart, or we want to use this chart, whatever, right? But sp3 we know has four groups, right? Three groups, two groups, right? Using the group method. And we know that lone pairs are counted as groups as well, right? So don't forget that. That's probably the main thing with if you're using the group method, don't forget about the lone pairs, right? Because that'll really throw you off. Um, so don't forget that. So yeah, good summary, right? Good, what's it called? Good chart, if I do say so myself. But yeah, feel free to use it definitely. Or I always like. Hopefully you guys are taking notes. Hopefully you guys are. You know, I like to do my notes pretty much make everything fit into one page, front and back, right? So when I start reviewing, you can just glance at it. And then on your peripheral, you can see other stuff too, right? So you're kind of studying two things at once. I don't know if that works for you guys. I know it works for me. Seeing it all on one page, right? I could be focusing on the top page, and then I'm pretty sure you guys, when you guys are studying, is like, and you guys done the test, you guys are probably like, this was on the top page of my notes, and then you can kind of see, right, like some kind of photographic memory type thing. So that's what I do, and also lots and lots of colors, right, highlighting things like that. So I'm pretty sure you guys, your handwriting and stuff, your calligraphy, your penmanship are much better than mine. So you guys can probably make it look 1,000 times better. So, and please do. Okay. So now let's move on to our. Actually, this one. Let's wait a second. So this one, this bent here still stays 120, but over here it kind of deviates a little. This is 107. This one and this bent is about 105. So nothing too crazy, but just know that they're not 109.5, right? So okay. So with that being said, let's move on to our next one, which is let's see. Oh, actually, no, I have questions. Okay, what am I doing? Okay, hybridization. It was covering the page was covering my question page. So molecular geometry. And again, we can do these for stuff that aren't carbons, right? On the examples, we kind of just did carbons, but we can do it for other atoms as well. But same thing, right? So here, um, find the hybridization and of these. So this one, of this one, of this one, and then this one, right? Okay. So do your thing. So again, you guys, well, actually, not just for these, actually, even for the rest of the questions, these questions can be twisted, manipulated, picked apart, right? And this one, I'm asking about the hybridization, but we know that once we find the hybridization, we know the bond angle, we know the bond shape. So lots of different ways this can be asked, right? And we can even do that right now, and we will. So this one, you guys should have gone SP, SP2, SP3, SP2. This one, SP3. Now we can get the shapes for these, right? Linear, and let me change the color so it doesn't get too muddy. Um, so linear, right? And what's sp2 over here? Trigonal, right? And then tetrahedral, This one, trigonal. This one is bent, right? Bent, tetrahedral bent, right? Because of those lone pairs. And now we can even go further and do the angles. And we can do that as well. So, get the most out of these questions by, again, kind of taking them, twisting them, kind of breaking them down, right? Or also, these questions are also hopefully are sparking like, oh, you can also ask this if these are, the types of questions that can be asked, so things like that. So always like think ahead, right? So linear, of course, 180, trigonal 120, tetrahedral 109.5, trigonal 120, bent was 105, right? So boom, this was like what, 3, 6, 9, 12, 15 question at once. We're good. Okay, so, and that was colorful as well. So again, colors are good. Okay, now we have condensed skeletal structures. So basically for these, not too crazy, condensed structures are your, like the chain, like CH3, CH2, CH whatever, right? And your skeletal is the big one because, and I'm just gonna do it under here. Points and edges are carbons, right? Hydrogens are not shown, but charges are obviously. Charges, heteroatoms are shown, and H's are shown if they're bonded to a heteroatom, so like NH, OH, things like that. And condensed is just like the chain. I don't know how to explain it. Just like the long chains written out. I guess it's condensed written out. Okay, so let's do some examples. And again, the trick here, or I guess the takeaway is that be able to go from skeletal to condensed, condensed to skeletal, like pretty much instantaneously, right? So that's the goal. And you will, because pretty much most of the time you'll be working with skeletal structures like as this goes on. So um, but you'll get used to it. So that's good. But again, definitely practice it and, you know, just turn everything. I like using skeletal structures, so I turn everything into skeletal structures because it's the most easiest and it's the most the shortest, like the most shortcut, right? So I like using skeletal. So I'll have questions for you guys. So turn this into condensed and skeletal, right? So turn this into condensed and skeletal, and then this one CH32, CH2, um, CH2, CH, CH3. Which one of these are it? This one, this one, or this one? So which one of these three matches this, right? Okay, so again, pause the video, do your thing, okay, and let's see what you got. Okay, so let's do it. Let's do green. For this one, you guys should have gone for the condensed CH3, CH2, CH3, or CH3, 2, CH2, right? So either or is fine. And this is like an even more shortcut way, right? Okay, and then the skeletal structure, you guys should have gone just literally like this, right? So we have three carbons, right? One, two, three, and the hydrogens aren't shown, so let's just mark them anyway, right? Hydrogen, hydrogen, so we're there. And we know there's three hydrogens because there's no charge on those carbons, right? So, but yeah, this is your skeletal structure. So that's it. So now, what's two? What do you guys get for two? You guys should have gone this one. And why? So I like to mark things. So let's mark them. CH3 2. So we have two CH3s, which is these two, right? And we'll probably use all these colors. And the CH over here, we have this is a CH. And again, I like colors, right? Coloring always good. CH2, this one, and then another CH, right? This one, and then that's Cl, of course, right? This one. Oh, this was supposed to be a Cl. Sorry about that. But hopefully you guys caught on with the other choices. And then, of course, last but not least, the other CH3, right? This one. So boom. And you see how the other ones, pretty much the other ones didn't have this one, didn't have the where this CH3 was, right? Isn't in the right place, and this one, the Cl, isn't in the right place, right? So yeah, pretty much, especially if it's long like these, you'll have choices, but depending on your professor, you may not, right? Just go one by one, right? Like what we did here. Bring colored pencils, things like that. Okay, so let's go into our last one. Our last one's bond polarity. Bond polarity. So pretty much CC bonds equals nonpolar, right? CH is nonpolar as well. And we know polarity is one polar bond, and dipoles reinforce. Nonpolar molecules, no polar bonds at all. Dipoles cancel out, cancel. So let's put that into practice, right? So, and you'll be using this a lot as well. Polarity is one of those great, pretty much like it's a great um detector because if it's like you can tell so much by just polarity, and you'll see later as the semesters go on how polarity plays a part, like in solubility, things like that. So bond polarity. So first one, label most and least polar compounds. And then we have CH3SH, CH3NH2, and then this second one, which one has net dipole of 0? Net dipole of 0. So let's see this one. Right. So these are double bonds. This one. Okay. So take a couple minutes, pause the video, and see what you guys get. So for the most and least, for the most, you guys should have gone this one, and for the least, you guys should have gone this one. And again, going back into electronegativity and stuff, right? I like to draw things, right? So let's draw them in our skeletal structure, right? So this is what it would look like. This one, CH3CO, right? And the carbon is obviously on the in the middle, right? CH3 and H2, right? So which one of these has the most, electronegativity difference, right? So SH or OH. So O is more electronegative than sulfur, right? And this OH bond is very polar, right? They're way apart on the periodic table. This one, carbon and Cl aren't very far apart in the periodic table, right? So the electronegative difference, the polarity is not as um, great as oxygen and hydrogen, right? And same thing over here, NH2, right? Nitrogen is not as um, electronegative as oxygen. And again, nitrogen out of all of these, right, is the um, least polar or least electronegative, right? Okay, now net dipole 0, you guys should have gone this one because these dipoles cancel out, right? These two reinforce, right? They both go this way. These cancel out completely. And these again reinforce, they both go down, right? So, and that's it. That's with the bond polarity. Okay, so with that being said, right, again, this is our agenda. Um, this is what we talked about. That's all I have for you guys, right? Hopefully that helped. Hopefully that solidified some questions you guys had. If you guys have any more questions, definitely go to your professors or SI and see if they can solidify that even further for you. Um, and for the rest of the semester, this is how the videos will be for OChem 1. So keep watching. Hopefully we'll see you guys later, and hopefully you guys tell your friends about it, and definitely take advantage of those questions because those questions are good, right? They're from a good source. So that's all I'm gonna say about that. So hope to see you guys around. Good luck. Bye.